Yeah.
works, but I'm not sure. I mean, in your next talk, because I'm
No,
not.
the next one's going to be completely different. So, yeah, no,
Because is it just that you take little segments of the resting state and
no. You take the whole resting state, you know, set.
yeah.
You look at the correlation between the resting state. Ooh.
Where you're going to be.
You know, the time series in one location with a correlation and another other time series. And so then the vector, instead of being a vector of responses to different parts of the movie,
Yeah.
or responses to different time points, is the vector of connectivity with all these different locations.
No, 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 no. Okay, that makes sense. Okay, I also read that as well. I thought you were making a vector out of each little bit of the resting, and then I didn't understand how it worked.
Yeah,
Okay,
it's
now.
connectivity.
Oh,
It's
yeah, yeah,
basically
yeah.
connectivity.
That was cool,
And
but I thought you
the
were
connectivity is for the whole
We're going to
resting
go on
state.
to Tom, and then he'll be here to answer
yeah,
questions
yeah.
after.
Got it.
So,
You know, it's a great class. Everybody's so eager to speak to you.
well, now I've got Swoop here, so Swoop,
That's right.
you can answer questions.
All right. So again, as promised, I'm going to move for a couple minutes, but I'll be back.
Okay.
You trust that you can use that.
What?
You trust that you can try that one too.
Yeah, it should work.
Surprised. I've had issues with different brands. And if possible, switch with these between your slides if you want. But if possible, you can use the mouse if you're pointing at stuff. Because
Oh, okay.
when we cast you, they don't see the screen, they see the screen. So if you
Okay.
use your mouse, if you need to point at stuff,
Oh,
use your mouse.
this for the talk. Got it. Yep, I can definitely do that.
Alice Caterina.
Huh?
Alice Caterina.
Dice Caterina. La piccola. 4 anni. 4 anni, sì. Sono matto. Ecco. Oh, this is. Let me do it this way. That work like that?
Thank you, yes.
Okay.
All right, since we're all back, let's keep going. I don't need to reintroduce our next speaker. So let's enjoy the second one.
Okay, that's good. That's on. So I assumed that you really didn't want to hear me talk for 2 hours about hyperalignment. Yeah, but I prepared. I have another talk that I often give on a related topic, but this is sort of the other half of my career, which is how do we understand the representation of high-level vision, especially in the object vision pathway. And we have we've been thinking about this for a long time. And come to the conclusion that a lot of the way we think about the functional organization in ventral temporal cortex is wrong. Okay, so again, it's the same usual suspects who are working with this on me. I should have a picture here also of Ida Gobini, because she and I are doing a lot of this work together. So this is an outline for what I want to talk about. First, we'll talk about most models or discussion of the organization of ventral temporal cortex focuses on the neural representation of faces, bodies, and objects. And generally, it looks like this, the ventral temporal cortex is optimized for person perception. So it plays a very large role in social cognition. And we'll talk a little bit about how, some of the is that me? This, it's from outside, okay. Evidence that the ventral pathway is specialized for spatial perception, especially for face processing. But then I'll show you a variety of examples for why we think are problems with this model. And specifically, there are two major types of problems. One is there's a big stimulus sampling bias, which is, and then the second is that the computational methods are inadequate to really understand what we think the organization in this area is. So first, let's talk about, in what way is the ventral temporal cortex optimized for person perception, and specifically for face perception. Now, this is a classic study from Simon Thorpe's lab, and it shows the saccadic reaction times, choice reaction time when subjects see a display with a face on one side and some other kind of object like a vehicle on the other. And the task is look at the face. These are natural scenes in complex backgrounds. And what they find is that when people are asked to look at the face, they have much faster saccades than if they're asked to look at the object, like the vehicle. And that they get reliably accuracies above chance as fast as 100, 110 milliseconds after the stimulus onset. Now this, I think, still hasn't been fully digested. This is blazingly fast and doesn't make any sense when you look at things like the ERP literature, because the response to faces, the fastest evoked potential to faces has a latency of around 170 milliseconds. Maybe there's one at 110, but this is actually an eye movement, which takes an additional 20, 25 milliseconds to initiate after the face has been identified in 110 milliseconds. Now, face neurons in monkey cortex have a faster response latency than neurons that are selective for objects or places over here. So this is work from Bell et al. And then this is a study by Visconti Diolegio Costello and Gobini, where they took Simon Thorpe's method and they looked at saccades to familiar faces as compared to unfamiliar faces. So how quickly can people make a behavioral response that reflects that they've detected, in some sense, which face is familiar and which one is not? And when it's a familiar face, they have saccades that are reliably better than chance at about 180 milliseconds. Now this also just poses a real challenge, because the fastest evoked potential that distinguishes familiar from unfamiliar faces is at about 230 to 240 milliseconds. So that's inside the brain, but somehow the saccade is able to make that decision 50 milliseconds faster. Let's see, these early face selective neural responses are not affected by attention. I won't go into details on this. This is a study that we did using MEG. And then we know that faces break through interocular suppression using continuous flash suppression faster than that upright faces break through faster than inverted faces. So in this paradigm, different images are presented to the right and left eyes, and the image in one eye is a dynamic, rapidly changing stimulus that grabs the visual system, and the stimulus it's coming into the other eye, it's making it into the retina and getting into the visual cortex is not consciously perceived. So the question is, how much processing is occurring for that stimulus that's been suppressed by intellectual suppression, even though there's no conscious awareness of it? And that's usually indexed by looking at how fast does that suppressed stimulus break through the suppression. Because the only way it's going to break through is if something, it's somehow being processed at a subconscious level. And what, in this work by Shang He, they found that the upright faces broke through much faster than the inverted faces. So even though the face stimuli were subjectively invisible, if they were upright, they break through faster. Now, building on that, Gobini looked at whether or not faces that are looking at you break through faster than faces looking away from you, or do faces of friends break through faster than faces of strangers? And in both cases, she found that was true. So again, there's all this processing of faces that's super fast, much faster than for other objects, doesn't seem to be affected by attention, and even occurs without subjective awareness. So that suggests that this whole system for face processing is optimized for being very efficient and fast and not requiring awareness or attention. And then we know that the extrastriate cortex has a set of patches that respond more to faces than to other objects. So in the human brain, in posterior cortex is the fusiform face area, the occipital face area, and the STS face area that respond more to faces than objects. And then in studies in monkeys in which they did fMRI studies to look at whether or not there were patches of cortex that show a stronger response to faces than non-face objects, they also found these patches. And again, they found a set of patches that they find consistently across monkeys, starting posteriorly in PL, then the intermediate ML, MF, and then AL and AM areas. So there seems to be a system, a set of areas, fields of cortex, that are responding more to face and are playing a special role in face perception. So this is a nice story, and this is the dominant story in how ventral temporal cortex plays a role in face perception. First, face processing is fast, requires mental attention awareness, and it's mediated by this distributed neural system in both humans and monkeys that seems to be specialized for face perception. So why am I up here saying there's something wrong with this? This is a beautiful story, but there's a fly in the ointment. And so this, how many people recognize this? It's terrible. Mothra, this is Mothra. You have to go back and watch the movie Mothra. A big fly. So what's wrong with this story? Well, first of all, it's based on experiments that are designed to test focused hypotheses that are driven by the investigators' theories and notions, and necessarily you can't have subjects look at everything. You can't test the responses to everything. So people are looking at, is there some special system for face and person perception? So they look at people's responses to images of faces and bodies and things like that. It's natural. You have to make choices as an investigator. You have to select some stimuli. You can't show everything. But is there a problem with that? Well, now the sampling bias is that this whole system, this model, is based on studies that use still images. And necessarily, they use a limited range of categories, generally faces, bodies, and isolated single objects. The second problem is that the computational methods for data analysis and model are based on univariate contrasts. And they ask the wrong question. They ask, what is the function of an area? So when identifying a face area, they say, well, this area responds more to faces than everything else, so it must be specialized for faces. So that's its function. And that's a very impoverished way to think about the tuning function for a patch of cortex. And I'll go into details about why I think that's a problem. Now, how many of you, I'm sure most of you have seen these animations before, right? These are the hydrosymbol social animations. And what's the difference between what you see going on over here and what you see going on over here? Yeah. So these two triangles seem to be having a fight, right? So there's a narrative, a social narrative that you just spontaneously attribute to this motion stimulus. Whereas these triangles just seem to be bouncing around mechanically, and you don't attribute any kind of intention or social interaction to them. So these stimuli have been used in a lot of MRI studies, dating back to this work from UCL. Castelli was the first author in this paper that came out in 2000. And they found that medial prefrontal cortex and this posterior STS area responded more to the social animations than the random mechanical animations. Now, what people have overlooked when they looked at these studies that there also is this other area here in the fusiform gyrus. It's even in the lateral fusiform gyrus, and the coordinates look really a lot like the coordinates for the face area. Now, the stimulus has no face, has no form in it at all. It's just triangles. So there's no face form in there, but there's social content. So what's that about? Now, in a follow-up study, Gobini et al., or in replication, used the same stimuli and found again that the posterior STS, and actually all along the STS, the response to the social animations was greater than the random animations, going into orbital frontal, inferior frontal cortex, and some pieces in medial prefrontal cortex. But it extends down into the fusiform cortex. And this actually has been shown repeatedly. And in a study by Schultz at Yale, he did the face localizer and the social animations and showed that the activations for social animations and the face localizer overlap. So in the same study by Gobini, she also had people looking at point light displays of motion and showed what others have shown, which is that these point light displays of motion also evoke a strong response as compared to random motions or scrambled motions in lateral fusiform cortex. So there is this piece of cortex that is really close to or overlapping or identical to the face and body areas in fusiform cortex, but it's responding when the stimuli contain no biological form like triangles, or only have biological form that's inferred from the motion in point light displays. So the idea that this area is sensitive to the form of faces and bodies is belied by these studies. Now, making this matter even more difficult is the work from another Schultz at Yale, working with Greg McCarthy, and they had subjects looking at videos of industrial robots doing robotic things, building stuff, okay? And they had some robots that looked kind of animal-like and some robots that didn't have any look at all animal-like. And they were either doing random motions or they're doing, they had a more goal-oriented motion. And what they found was when people were looking at robots performing goal-oriented actions, they got all this activity in ventral temporal cortex, including lateral fusiform cortex. So I don't have one of their videos. I just pulled this video off the web of something that's putting fan blades in a fan. It's a three-armed thing, but this is the kind of thing, when people see something like this, it activates the same, these same cortical fields in ventral temporal cortex that are associated with perception of biological form, like faces and bodies. So this is a problem. Now, The next study I want to show is the study that I talked about in the last talk by Sam Nastase, where it has people looking at these videos of animals doing different kinds of actions. So here we have ants and seagulls and baboons, and they're all running, okay? And now there's the gorilla, the hummingbird, and the caterpillar. They're all eating. And you can also have primates doing different things. So these are all primates. So there's a baboon running and a gorilla eating and a couple of baboons fighting. So now they share the taxonomic category and they don't share the action category. And here are 3 species of insect. I love these videos. That's why I show them so much. Because here's a ladybug fighting with an ant, and here's the caterpillar eating, and here's some kind of beetle running across the ground. So what, in this study, what the subject had to attend to either the action or the taxonomic category. And with each new stimulus, they would indicate whether or not, in some blocks, they would indicate if the action was the same as the previous action depicted, or was the taxonomic category the same. And these are broad taxonomic categories: insects, or birds, or ungulates, or primates. And then he analyzed this using representational similarity analysis. And he broke this down into 2 target or model similarity structures. In one, it's looking, it's saying, are the responses to the same taxonomic category more similar than responses to different taxonomic categories? And the other, this one over here, they're asking, are the responses to the same action more similar than responses to different actions? So to what extent are the patterns of response more similar for primates as compared to primates as in contrast to primates versus insects? The other is, how much are the patterns of response more similar for eating versus eating as compared to eating versus fighting? Okay? And it's a complicated paper. I hope it gets published soon. But what I want to point out here in the context of this talk is something that really surprised us, and that is that this model similarity structure was a much better predictor of the representational geometry than the taxonomic category. We've been laboring away studying taxonomic category for years, and now Sam comes along and shows us that that's a small part of the story. The big part of the story about what's going on in the brain is what is the response to the behavior you're viewing rather than what is the type of animal you're looking at. So this shows the variance accounted for, partial R squared, accounted for by the behavioral model and the taxonomy model. So you can see the histograms, the bars for the behavioral model are much higher everywhere. Oh, geez, Louise. There. In all these different brain areas, VT is ventral temporal cortex. Oh, geez, I'm sorry. There, okay. Okay, we good? Are we good? Yeah, we're good, okay. So the amount of variance explained is much higher. It's over twice as much variance as accounted for, but even in ventral temporal cortex. Now, this is something that's really surprising, and people are having a hard time accepting it, that in this particular study, we're finding that the representational geometry reflects representation of behavior, the actions of animals we're looking at, more than the type of action. So motion more than form, but a specific kind of motion that depicts the intentional behavior. Now, this is now a study of responses to dynamic natural movies that Brian Russ and David Leopold have been conducting for several years now at NIH. And so they have regressors from their movies about when are there faces in the movies and what is the amount of motion energy in the movie. And how good are how much variance is accounted for by the presence of faces, how much variance is accounted for by motion. And you can see this is much redder. So the motion is accounting for much more variance than the presence of faces. Now here are the face patches. So this actually is a very nice face patch localizer, just having the monkeys watch movies of other monkeys doing monkey things. And they can identify, here's PL, ML, AL, in the face patch system. But if you look at the variance accounted for in PL, ML, MF, AL, AM, the amount of variance that's accounted for by motion is much more than the amount of variance accounted for by the presence of faces. So again, their results don't contradict the earlier results showing that there are face patches that are more responsive to faces than other stimuli. What they're showing is that the response tuning functions in these patches is actually reflecting more the motion than the presence of faces. It reflects both, okay? You have to keep this in mind, that I'm not saying it's not either or. It's both, but one is more than the other. And they ran a control that shows that the type of motion is biological motion. It's not simple motion energy, because when they had videos that had a lot of motion energy, but with no animals, they didn't see this kind of effect at all. It was only the response to the biological motion of the monkeys that showed this. So, here are two more pieces of evidence that in the ventral temporal cortex in humans, in the face patch system in monkeys, it seems to be responding more to action and behavior, or more strongly representing action and behavior than it does form, even though the models I've talked about before are all focused on the representation of the form of faces and bodies. Now here's another study by Fairhall and Gobini that's also under review, where they had congenitally blind subjects listening to voices. And they looked at whether they could decode the emotional content in the voices, and where in the brain could they decode that information carried by the voices. And what this shows is that in the FFA, in the blind subjects, you can decode the emotional content of voices. So these are people who have never seen a face. It's impossible to identify their face area because you can't do a localizer study with them. But whatever that patch of cortex is, in lateral fusiform cortex, that has been deprived of visual input, the function it's assuming is a function for representing information from voices about other people. Okay? So again, it's just dissociating the representation of form, facial form, body form, from the representation of social content as conveyed by voices or behavior or the motion of abstract animations. So lateral fusiform gyrus is evoked or modulated by moving triangles in the hydrosymbol animations, moving points of light and point light displays of biological motion, industrial robots that have no resemblance to biological entities. It responds more to animal behavior than it does to animal form, or represents more strongly. And it can represent voices in the congenitally blind. So the sampling bias for previous experiments that used only still images of limited categories of faces, certain types of animals and bodies has restricted the understanding of the functional architecture. So what is represented in fusiform cortex? Is it animate as compared to inanimate entities, or is it agency? So let's address this first question first. So is the animate-inanimate distinction the major large-scale feature here? So it doesn't have to do with the form of faces, the form of bodies. It has to do with, is the subject perceiving, representing animate entities? And this has an old history too. So in the reanalysis of our 2001 data on representation of faces and objects in ventral temporal cortex, Alice O'Toole and Hervé Abdi did a similarity structure analysis, and showed that the representation of faces in cats was distinct from the representation of the inanimate categories. There's this beautiful study by Rusbek-Kiani looking at single unit response, population responses using single unit recording in IT cortex of monkeys, and showing that the population responses show a similarity structure where the major distinction is between animate and inanimate. So there are these animate categories of different kinds of faces and bodies. And Krieges-Korte took the data of Kiani and then got some fMRI data using the same stimuli and showed that the biggest distinction in the representational space in human ventral temporal cortex also was the distinction between animate and inanimate. So that seems to be, and then in the paper by Grill-Spector and Weiner, they hypothesized that there are these nested representational distinctions in ventral temporal cortex, and the overarching one is animate versus inanimate. Animate being lateral, inanimate being more medial, and then you have representation of faces, body parts, eyes, and things like that nested within the animate domain. Now, the problem, this is a nice story too, animate versus inanimate. This is, again, is dominant, and if you hear other speakers, they're going to talk about that as a major organizing principle in ventral temporal cortex. Andy Connolly ran a study in our lab where he looked at the representation of these 6 species of animal, 2 species of insect, 2 species of bird, 2 species of primate. And he found the dominant dimension in the representational geometry had primates on one end and bugs on the other and birds in the middle. So this, he called this the animacy continuum because the bugs were on one end. And if you look at the contrast of primates versus bugs, okay, in the pattern of response, this is a univariate contrast. The primates evoke stronger responses laterally, and the bugs evoke stronger responses medially. So it's blue here because it's lower than the response to primates. So this topography, this univariate map, looks exactly the same as the topography of faces versus objects in the same subjects. So this difference between primates and bugs looks like animate versus inanimate, but nobody in his right mind would say that insects are inanimate. It's just that we think about bugs very differently from how we think about primates and mammals and even birds. So Longshot did a follow-up study where he had primates, mammals, these are cats and giraffes, birds, he had lobsters, stingrays, ladybugs, and clownfish, and then hammers and keys. And found the animacy continuum, again, with the primates on one end and the lower order things like bugs and fish on the bottom, and the birds and non-primate mammals in between. But the keys and the hammers really overlap with the low animacy entities. So we thought, when we set this experiment up, that we were going to show that all the animate things were on one end with an animacy continuum, then there's going to be a big gap with the inanimate things way over on the other end, replicating the animate versus inanimate distinction. Instead, we got this result, which was really surprising, but suggesting that really the animacy continuum the animate-inanimate is really a special case of the animacy continuum and only reflects the distinction between objects and the higher order animals like primates and mammals and birds, and not the lower order but equally animate animals. And again, the topography for the primates versus objects is exactly the same as the topography for the animacy continuum of the animals other than primates, and not including the keys. So this suggests that the animate-inanimate dichotomy is actually a special case of a broader principle the animacy continuum. And the animacy continuum actually has a very deep intellectual history. Aristotle, in his treatise on the soul, talks about an animacy continuum, starting with low-level things like clams, and then proceeding upwards to humans, but then humans are superseded by the gods. And actually, animacy hierarchies play a role in linguistics, too. So people use different linguistic grammatical forms in many languages for things that are high animacy versus low animacy. And we even do that. So if we're talking about people, we always use he or she. But if you talk about things like bugs, you're very comfortable saying it, right? And that's this conditioning of grammar based on the animacy continuum is even stronger in other languages. And then there's also something called the Great Chain of Being, which is also the animacy continuum, which is considered another organizing principle in thinking around the late 19th century. So, is the animacy continuum the dominant organizing principle of ventral temporal cortex? Well, there's some problems with that too. So what is the animacy continuum? So high animacy things have more complex internal states that are driving their behavior. So it's a more complex level of agency. So is it the level of agency in the stimulus that is being reflected by this pattern of activity in ventral temporal cortex? So Gobini, proposed that in 2007, but then in a later paper where she had people looking at robots and that she found the same type of distinction, she says it's the representation of agency that's independently of whether the agent is living or not. So it can be agency in non-living robots. And Schultz and McCarthy come to similar conclusions in their paper. So is this it? Are we starting to narrow it, close in on what is the organizing principle? It's not faces versus non-faces. It's not animate versus inanimate. Is it the level of agency, the sort of natural perception of whether something is agentic? Well, I'm not satisfied with that either. And so now I want to go have a little digression. I said I wouldn't talk about hyperalignment, but I talk about here. It comes from the work on hyperalignment. So again, this is the patterns of response while people are watching Indiana Jones. And the idea is that with each new time point, we have a different, a new vector. We measure a new vector in the representational space. And that we derive this transformation matrix so that we can now have a common model space for responses to the movie. Now, there are two important things here that I want you to keep in mind. The first is that we're using a very different kind of stimulus. So instead of having a limited number of categories that we pre-selected based on our hypotheses, we just let Steven Spielberg make all of our choices for us. And people watch the full movies. And the second is that we're deriving this common space that's high dimensional. So how high dimensional is the space in ventral temporal cortex that captures the variety of responses to a more natural movie? So when we look at between subject classification performance for the top 5 PCs, so we did a principal components analysis and reduced the number of dimensions. When we look at just the top 5 dimensions, classification performance is down below 50%. Then it jumps up to around 62% with 10. And you really have to get up to over 30 before it's starting to show optimal performance of about 68% accuracy. So we can reduce the space from 1,000 voxels or 1,000 dimensions down to about 30 or so dimensions and capture all the variety of responses to the movie in that space. But it's not 2, it's not 10. Now the animacy continuum, or the animate-inanimate distinction, is a single dimension. That would be a one-dimensional space, okay? So that one-dimensional space is not capturing the variety of responses in ventral temporal cortex. We need more than 30. Now, we toyed briefly with the idea of saying, because it's pretty arbitrary where we say, how many dimensions do we really need, right? So we thought we were going to just say 42. But how many of you know that, where the number 42 comes from? There we go. Mark's hand went right up. Hitchhiker's Guide to the Galaxy. So I think the magic number might be 42, but we're not sure about that. So that means that these low-dimensional spaces, like the animacy continuum, don't account for very much of the variance. Now, when we look at the topographies with these PCs in ventral temporal cortex, the first PC is just picking off these two little spots, or just a couple little spots here. These are inside the FFA, but they're a very small part of the FFA. We don't really know what this PC is, but it accounts for a lot of the variance in responses to the movie. Now, this seems to have the animate versus inanimate, lateral versus ventral distinction in PC2. But you don't really see face areas in these PCs. So this shows the location of the face areas in these two subjects, superimposed on these maps of the PC weights, these topographic basis functions. And you can see that none of these top PCs is picking out the face area as something that's distinctively different from the rest of ventral temporal cortex. You can derive that as a weighted sum of these topographic basis functions and then get a very nice prediction of the location of the face areas based on a weighted sum. So maybe we just had the dimensions rotated the wrong way, and if we rotated them, so we picked up that particular dimension that has dominated the discussion of the functional organization of ventral temporal cortex, we find that was dominant. So we did that. We looked at how much variance is accounted for by this dimension, accounted for by faces versus objects or the animacy continuum. So this shows the variance accounted for by the first PC, second, up to 35 PCs. So the first one is about 21%. The 1D model, faces versus object linear discriminant, accounts for about 7 to 8%, okay? So the face versus object linear discriminant accounts for 7% of the variance, less than 20% of the variance accounted for by the first three PCs in this complicated space, and less than 13% of the variance accounted for by all 35 PCs. So it's a much more complicated space than is captured by something like faces versus objects or animate versus inanimate or the animacy continuum. A single dimension just isn't accounting for very much. So let me try to drive this home a little bit and bring back the idea of stimulus sampling bias. Because remember, what we're accounting for here now is the responses to the movie. We're not accounting for responses to still images. If we look back at our data from Long Shaw's paper, where he did have still images of these 10 animal species and hammers and keys, and we do a scatter plot of the variance accounted for, the first dimension accounts for a much larger portion of the variance, okay? And this first dimension has the topography of the animate-inanimate distinction or the animacy continuum. So when you look at the variety of responses to still images, that particular dimension is accounting for more of the variance. But as soon as you use a more natural dynamic stimulus, it's a much smaller portion of the variance. And even in that study, the first PC captured the between-class distinctions. So that's primates versus lower-order mammals versus birds versus fish versus bugs, okay? But did not capture the within-class, so people versus chimpanzees or warblers versus pelicans. Those within-class distinctions were only captured by the lower-order PCs. So you need a high-dimensional space, even in that representational space defined by responses to still images, to capture those finer distinctions. So is the animacy continuum, so varying levels of agentic complexity, the dominant organizing principle for representation of ventral temporal cortex? Not exactly. The animacy continuum face object distinctions, which are really collinear, account for only a small portion of variance in responses to a rich natural dynamic stimulus. And the animacy continuum and face object distinctions account only for coarse but not fine-grained distinctions in this representational space. So let me summarize what I think what I've been trying to say here. First of all, there's a stimulus sampling bias. So studies have been dominated by looking at the responses to still images from limited pre-selected categories like faces and hands and bodies. I regret using Chiani's stimuli because this is a very rich stimulus set of still images as compared to these kinds of dynamic stimuli like the hydrostimal animations, robots, or behaving animals. So these category-selected regions have more complex tuning functions that suggest they play more diverse roles in person perception. And the representational geometry is dominated by the representation of behavior, not by form. And the inanimate principle is not the principal dimension that characterizes the coarse lateral to medial topography and ventral temporal cortex. So, in a sense, this is like the blind men and the elephant. Now, the legend of the blind men and the elephant is 6 blind men are sitting by a river and they sense the presence of something large in their midst. So they go to investigate. They can't see what it is, so they have to touch it. So one blind man touches the tusk and says it's a spear. Another one touches the tail and says it's a rope. Another one touches the leg and says it's a tree. Another one touches the side and says it's a wall, etc. Now, all of those guesses make sense from what they are able to obtain from their sense of touch. But because they can't see the whole animal, and they can't put all those features together into the totality of an elephant. And in a sense, when we think about ventral temporal cortex and try to approach that with experiments based on limited stimulus sets with limited computational methods, it's like being blind because we don't have adequate stimulus sets, we don't have adequate computational methods to see the totality of ventral temporal cortex. That yes, things like the animacy continuum, domain specificity, animate versus inanimate, category selective regions, all those things exist in ventral temporal cortex, but they account for only a small portion of what's going on there in ventral temporal cortex. And you need better designed experiments with natural, richer stimulus sets and computational methods that let you model it as a high dimensional space rather than stimulus selective regions. So the computational methods are inadequate because they use univariate statistics. They search for the function of an area rather than try to analyze what is the representational space in an area. Whereas multivariate methods like pattern classification, representational similarity analysis, hyperalignment, they model the functional architecture as a high dimensional representational space. And the topographies for these dimensions are multiplexed and overlapping. So instead of looking for an area, we look for a variety of topographies that are multiplexed with complex tuning functions at any given location. And this kind of a model can account for category selective regions as well as the fine-grained patterns that carry fine distinctions in these areas. So that's what I want to say, and I want to say thank you for your attention.
Everybody knows the mantra stimulus. Any hands up in the air here?
You're intimidated. Okay, there we go.
Hi. Might sound a little stupid or odd, but do you think this contingency could also be related to the value that humans usually ascribe to these objects? You know, that like a mammal or something that is more familiar to us that we ascribe
Yeah.
a higher value, like emotional value?
Yeah, so we have not done a systematic analysis of exactly what is the animacy continuum. One hypothesis is it has to do with complexity of agentic behavior. But familiarity clearly plays a role. So for example, the cats are much higher in this animistic continuum than giraffes, right? And we're much more familiar with cats because we live with them. So we think that familiarity probably plays a role. And value, I mean, I'm not sure exactly, but yeah, how important do we think, cats are as compared to giraffes or fish? Yeah. So that needs to be systematically analyzed. I'm still pretty comfortable with the complexity of agentic behavior as a good initial hypothesis. Yeah.
Hi, I still have a question on hyperalignment. So, I'm sorry.
They just keep pulling me back in.
So I wonder, so if I really interested in the individual difference.
Pardon me?
Individual difference.
Individual differences.
Yeah. If,
Okay.
If
Yeah.
I'm really interested in this domain, then is the hyperalignment still suitable? Because the way I understand it is that it diminishes the individual difference in the functional activity pattern.
So thanks for asking that question, because I was, this is something that people always bring up, which is, can we start to look at individual differences in the common model framework? And the purpose of that project, building the common model, was to find what's common across brains. And we succeeded in finding a lot more commonality than we even expected. Does that mean that we've eliminated differences, or are there still differences? And so we're starting to analyze that systematically now. And there's a graduate student in the laboratory who's looking specifically at that. And the first question he asked is, are there reliable individual differences between subjects based on their representational geometry or based on their patterns of functional connectivity? And so you can get an index of how similar two subjects are by vectorizing all the functional connectivity vectors or vectorizing all the representational geometry vectors, and then just looking at the correlation between subjects as a similarity. And so some subjects are more similar than others. So now we have a subject similarity matrix. Some subjects are similar, some subjects are very different. And that subject similarity matrix is highly reliable across subjects. And so we thought, well, it should be less reliable after hyperalignment because we've eliminated a lot of the sources of inter-subject difference, like anatomical variability. We've tried to take that out of the equation. And actually, the individual differences are more reliable after hyperalignment than before, which is surprising. And so we think that, what we're finding is that that somehow this method, we don't understand why yet, is factoring out individual differences that we're not interested in, that have to do with differences in the locations of areas and sulcal folding and things like tidal folding. Take all that out, and we're getting a more pure measure of differences in functional architecture, either representational geometry or functional connectivity. And we're actually finding clear differences between subjects. And so now we're looking at whether, Fei Long, is looking at whether these differences are related to individual differences in things like task performance, IQ, and we don't have an answer yet. But yeah, so that's so we're actually really excited that this is going to be a way of getting a purer measure of individual differences in functional architecture and factors out anatomy.
Hi. This idea of multidimensionality is great, and I think a lot of people are moving into it. Even Alfonso will be moving into it, I think. But what strikes me is that when you look at the neuropsychological literature, category specificity, and you use images of animals, and those images of animals include primates, monkeys, they include bugs, and they are compared against keys and hammers. And what you see is a divide that is more about category or domain, if you will. So why don't we see category specific, or if you will, I don't know, semantic deficits that follow this type of dimension or other dimensions that could be underlying the organization and at the VT, but we see deficits that actually are in the divide between animals,
Yeah,
tools,
I think that if you go back to those studies, you'll find that they're dominated by pictures of mammals and birds, mainly mammals. Very few bugs are in them. And no study before ours has looked at the difference between the responses to mammals versus bugs. So they lump them all together. And so if you lump them all together, you're going to get, the average is going to look like the responses to higher order animacy. And that's why it looks categorical.
So you're making a strong claim that if you were so you're making a strong claim that if we were to go back to any of these patients, and if we were, say, a category-specific patient that has issues with, is impaired at recognizing animals, but not the typical way of looking at, not other categories. If we were to analyze this patient, and if you were to look at comparisons between bugs and mammals, you're making the claim that this person would actually be okay with bugs, but not with
Yeah.
or at least you would see that
I mean,
divide.
I'm just saying that's what we find. When we look at primates versus bugs, we get a topography that looks just like mammals versus objects. So I mean, if that's reliable, then you should be able to see that in other data sets if they were broken down according to those distinctions.
Yeah, so I have just like super general question. So I was just wondering to what extent your methods can be informative in how people learn these representations.
Yeah. Yeah, so we haven't done that yet, okay? Now, in Sam Nastase's study with the animal behavior and taxa, he had subjects attending either to the animal behavior, saying, is this a repetition of behavior, or attending to the animal taxa, saying, is this a representation of animal type? And when they did that, the representational geometry warped. So the distinctions that were attended became greater, the distinctions that were unattended became smaller. So we know that attention will affect these geometries on a short time scale. And we assume that learning will affect these dimensions in a more enduring way. And one study I would love to do, and I shouldn't tell you because I want to do it, and now someone else is going to do it. I would love to get a group of entomologists who study insect behavior, especially complex social insect behavior, and see if their representation of insects versus birds and primates is different, because I would suspect that people who study termites or honeybees are going to have a much different understanding of how complex those animals are than the average person.
It seems to me, looking at your stuff, an interesting question might be whether you can also build representational space is maybe not the right term for it, but a vector that also includes process and function. That is, this map isn't going to tell us how we do calculus.
Right.
And yet your representational space for all of these concrete out of the things out there in the external world manages to populate the majority of cortex.
Right.
And clearly we know that cortex has segregation of different kinds of function. I wonder whether you've thought about building an extended representational space that also includes process.
Yeah, so we have to kind of work on the vocabulary. We started saying representational space. because we were using representation of, visual categories or auditory categories, things like that, or visual auditory features. And we could warp that to say we're talking about the representation of addition versus subtraction, or logic versus estimation, or something like that. But I don't like, it would be better to come up with a different term to say that we're not just talking about the representation of a process, we're talking about the execution of processes.
We can forget the term, but think about the general geometric interpretation.
Yeah.
Extended to other dimensions.
Yeah. And the other thing that that brings up is what the model as I presented it is kind of it doesn't have time built into it. And so these processes unfold over time. And because we're using fMRI, and fMRI tends to be sort of a static picture of brain activity because of the temporal characteristics of the hemodynamic responses, we don't take time into account adequately. And I think that extending these ideas into modalities like MEG and EEG will force us to start thinking about how processes unfold with time, and how we can model these temporal processes in a common space.
We've spent in my lab time thinking about Markov processes and trying to look through what we're looking for, but transitions between states and a trajectory through some sort of a state space. And when I'm thinking about it in the context of your data, it's a little bit contaminated by the fact that the way you're making these things is already built-in trajectory that's informed by Steven Spielberg, right?
Yeah.
What follows what, and to go and unpack that when you're outside of a resting state would be kind of tough, I think.
Unpack the
this notion of a trajectory through these spaces of a time dimension, right? The time dimension is enforced by the nature of how you actually build these models.
Yeah, and so let's just say it's a real challenge.
Others? I imagine what's happening is everybody's just dying to get their hands on the lab right now, right? Because you all want to do this yourself, so this is great.
So that's next, right?
Exactly. Next.
Starting at 4 o'clock?
Starting at 4 o'clock, yes. And Swaroop, I guess, is going to be running that. I believe that everybody has the data that was downloaded. Anybody have trouble with that? I have a hard disk which has it on it in both PC format and Mac format, and the virtual machine and everything. Okay, good. All right. Excellent. Thank you so much, Jim, for
my pleasure. Thank you for inviting me.
Finishing up our course with us.
Yeah, I guess that was my question, actually. I feel like I'm talking. I mean, everyone can listen again. No, I think that's a really interesting point about the resting state. And
So one of the fun features of the course always has been the chance to go ahead and get your hands on the really latest and coolest software that's here. And Jim, in setting up to do this lab, went ahead and delegated to Swaroop, who you've already been introduced to very eloquently as one of the key developers of all of these tools. So we're extremely fortunate to have Swaroop Kuntapalli here to give us a demonstration of this toolbox. And this one is going out to the web, and so hopefully we'll have a lot more people watching over time. Thank you so much, Swaroop.
Sorry, Jim Haxby's lab. So hopefully an hour and a half is probably not the amount of time required to make you experts in PyMVPA, but I'll try to get you the basics and see if we can pick up from there on your own, in your own time. So the main two developers of the software package are Yarik and Michael. Yarik is a research associate in our lab at Dartmouth, and Michael is a professor at University of Magdeburg. Everything I'm going to talk about today and all the analyses or the tutorials or the notebooks we're going to use for the tutorial are available on the website, pymvpa.org. So you can basically go there and do it on your own. And I can just like help you whenever you have a question. And other big thing here is the basics I hope you guys are probably already familiar with. If you know some programming language, probably MATLAB or Python would be great, but all you need for this particular kind of tutorial is the very basics of Python. And even if you don't know Python at all, it's fine because it's very easy language to understand and learn. And you wouldn't have like if I run like say a print command, it's like you know what it's doing, so it's not a big deal. The other package is a set of packages called NumPy and SciPy. I'm pretty sure most of you are probably familiar with it. They are basically a set of mathematical tools most people in the scientific community use, and most of the commands you use or functions you use are very similar to what MATLAB calls them. So if you are familiar with MATLAB, they're going to look pretty much the same. And the other thing we're going to use is an IPython notebook. So it's essentially something you can enter your commands in a web browser and then execute it and then look at it interactively. Just makes everybody's life easier because you don't have to complete your full script and then run at the end and see something is wrong. So you can basically take it step by step and see how the results look in every step and go from there. So I'm hoping all of you guys have virtual machines installed. And do you also have a PyMVPA on it, or you don't know yet? Wait, okay. So the best way to know if I can probably come and help people who don't have it, but if you have virtual machines installed and if your computers are all connected to the internet, one thing you can do is open your terminal. Well, actually, you can. Let me actually show the virtual machine I have. Damn it. Sorry. So if you have that up, then you can go to System, Synaptic Package Manager. You just enter Neurodebian there, all small. And you can do a search for PyMVPA. So it's like the start menu stuff. Oh, you mean the Neurodebian? You should have something like that. Sorry, an Oracle VirtualBox, which, yeah. And then you basically click on that, and then say start, and it should open the desktop in a window, right? And then, but like, anyway, so if you have the virtual machine, you can probably do this and look for PyMBPA. If they're already marked, like in my case, that means you actually have PyMBPA installed, MBPA to install. If you notice, I also have these two, which are documentation and tutorial data. So documentation contains all the tutorial notebooks we're going to use today, and the tutorial data contains all the data we're going to use today. So if you have all the 4 things checked, you're good. If not, you can check and say apply, and I don't know how long it takes, but it should be downloaded in like a few minutes at most. Or I think you also have the link for the tutorial data on the course site, so you can as well download that. But the PyMBPA software and the documentation are pretty small, so they should just you can download them within like a minute or so. So so if you can start the download now, and I'll just go through like basics of the software, so which do not involve notebooks yet. So if you have 5 minutes or 10 minutes, you can just start downloading enough or installing it enough. So is that clear? Let's see. Oh, I'm saying like if you don't have it installed already or downloaded the documentation or tutorial data sets, you can start now and let it download in the background, because I'm going to go through some slides for maybe 10 minutes or so it should be done by then. So I'm assuming like you guys have, you will have a setup eventually. I'll come and help you guys if you have any problems with that. But the basic plan for today is going to be, I'll introduce the concept of data sets, which is the key idea in PyMBPA, and then we go through another concept, an important concept called mappers, and then we do some exercises in IPython notebook, which should make you familiar with how to work anything in PyMBPA, like some analysis you want to run of your data sets. And we have, I think there are a lot of notebooks available on the PyMBPA website and the documentation, but due to the time constraint, we're gonna I'll try to at least go through like these 5 notebooks. And probably not every step, but some of the important ones that are critical for understanding what's happening. So let's start with the data set. So most of the data you're gonna use can be viewed as an n-dimensional array of numbers, right? It's just like a bunch of floats. So let it be like a matrix. I'm just showing 2 dimensions, but that you can pretty much change any data into a 2-dimensional data set and work with it. And especially true for fMRI data set. So PyMBPA has this concept called data set, which encapsulates that idea of like an array or a matrix. And then the rows are usually called samples, and the columns are called features. And we can see how this actually translates to fMRI data set. So if you have an fMRI data set, then the rows would be either TRs or your beta maps or statistic maps for stimulus categories. And obviously the features are going to be voxels. But these are not restricted to be voxels or TR. So for example, if you already ran a GLM of your experiment, you can just use the beta maps for your categories in the experiment. And the voxels features could be channels in EEG or MEGs, like data sets, or you can also use, let's say, mean of an ROI. So the features could be like ROI1, ROI2, and like whatever, 122 you chunk the brain up into, and then use the mean values as the feature samples. So that's the basic idea. Like there is this object called dataset. fMRI dataset is like a subset of the object, but the whole dataset concept is that it has a bunch of samples, which are like your TRs, and you have a bunch of features, which are like voxels. So once we have that, but the data array by itself is not very useful, because we need to know what they represent in terms of what each row represents and what each column represents. So a data set in PyMBPA also has attributes, which are like properties of those columns and rows. So for example, here I'm showing one column, which is a column of feature, samples from one feature. It can have a bunch of feature attributes. Those could be a location in the brain. So for example, for a voxel, it would be XYZ coordinates, or a surface, it could be like surface node index, and then ROI, like which region of interest it belongs to, or if it's part of a gray matter or white matter, or ventricles. So you can have all of these properties tagged to each column. And you can do the same thing with samples. So they're called sample attributes, obviously, and each of them could be like a TR number, or the stimulus category that the person is watching or looking at, or the beta. If it's a beta map, then it would be like the condition, the experiment condition. And it can also encapsulate things like run number, so you can have multiple attributes. So these could be very useful when you're doing analysis, and so that you can sub-select, oh, I want all the data from a particular category, from a particular set of features. You can just do that very easily with these tag to each of those rows and columns, which we will go through in the exercise. Oh, and also the data set on the total, it can have some attributes. Some things you can think of are like subject ID. Like if you have a bunch of data sets, you can have like subject ID and for each data set, and then you can also tag some history. Like for example, if you have a Nifty file that has come out of the scanner or analysis, it's 4-dimensional data set, right? So like 3 dimensions in the space and 1 dimension in time usually. But somehow we got that down into a 2-dimensional array, so we can kind of take the transformation we used to flatten that 4D array into 2D and keep it in our attributes, which actually what PyMVPI does when you load a Nifty file. So that will be very useful, because once you have some analysis done in this 2-dimensional framework and you want to map it back to look at how it looks in the brain, that you can reverse that transformation and then map it into the brain space in 3D or 4D, and then look at it in like FSL view or AFNI, whatever you like. So all of these things will help give meaning to what the data set is. So I think that's the basic start, and we can now go and look at IPython notebooks. So if you haven't already gotten them on your computer, you can go and, so all of the notebooks are also formatted as HTML files. So you can, if you go to that link, you can just see them as basically a bunch of like static documents, but we're going to use them as active ones and then go through it. So do you guys know where they are on your systems, or? Let me see. So if most of you guys have the Python MVPI doc installed, then I'll show you a simple way to actually find where it would be. So open a terminal. If you don't have it there, you can just always see it in here, I presume. And then just type in IPython. Hopefully that worked. And then if you do something like, well, let's see. So what this does is just imports the package MVPI2 into the Python environment. And if you do that, it should tell you where the package is installed. Just MVPI2 and question mark. Sorry, what? So if the import, and yeah, if there is no output, that's good. If there is some problem, it will just spit out some error or warning. So So one of the good things about IPython is that if you don't know what a particular object or function is doing, you can just like type the name of that. I don't know, like say print, and then I hope print works, but I don't know. We'll see. And append a question mark at the end, and it usually, well, it doesn't. But like for real objects, it usually does. So if you append a question mark, it actually tells like what it is and documentation associated with it. MVPA2 is a package, so it's nothing much interesting going on here. But one thing it does give you is this, so you know where things are installed. Yeah, so you can, oh yeah, sorry, when you exactly, so. And then you type Q to get it off it. So let's see. So now we have the IPython, sorry. Do you think it's easier to just distribute the notebook folder? Because I can copy them and give it to you if people don't have it. Let's see. So do you guys have an internet connection? So that, I think the best would be then, let's do this. So go to the oh, you have to do it in the virtual box, I suppose. Oh, it is. Yeah, I think there's a set of notebooks that I would like them to have.
So you sent us 2 files, 2 TARs.
Those are data sets.
That's what it is.
That's, no, I'm actually trying to get to the IPython notebooks, which I don't think I've sent.
You didn't send.
Yeah. Well, they're like actually online, so.
Oh, okay. Well, yes, we wouldn't have that address.
Oh, okay. It's okay. I think I'll, but they can all get online, right?
Have the 2 things you sent.
Oh, okay. Do you? Well, I think I'll ask them to download now if that works.
If you have a link.
Yeah, I'm gonna put it on. Do you guys have a browser in the virtual machine? Perfect. So open that. And try to go to PyMePI.org. And go to tutorial. So click on tutorial link on the home page, and then scroll down and click on the data set basics and concepts. Did it work? Perfect. So once you're on that page, there is a link on the top at the note. So if you basically right click on that, and then if you save link as, it usually saves it as a IPython notebook. No, it should be the the second one. So not this, but this. And you can save it wherever you want to work it up. Well, I actually have all of them saved, so I have them with me. So you can just create a directory called notebooks and then save all of them together. So once you save it, go back to your terminal. So I'm just going to exit this for now. And then go into the directory. So wherever you save the IPython notebook, go into the directory. And once you're in there, just type in IPython space notebook. And it actually opens the browser for you, and then it should technically list all of the notebooks you have in that folder. How many? Yeah, how many got it working?
How many have it working?
Yeah. Oh, wow. Yeah, so I'll just put it back. Oh God, that's.
We're getting air.
Did it exit?
It just didn't load because it says there's no module named Notebook on Notebook app.
Interesting. So you don't have the notebook installed. Well, so you can do what we did before, which is going to the System Synaptic Package Manager, the Neurodebian. Yeah, sorry about that. You can still do the exercise without the notebook, but you'll be in the console, and you have to type all the commands by hand, which is not fun. So if you search for IPython, you should be getting this thing called notebook, and then you can install that. So why don't I just go through the notebook, and you can either type those commands in or just follow me through for the first part. Is that okay? So it just saves us time. What you can do is you can just go to that link I've just showed, which is that one. And we're basically going to just go through that step by step. But instead of looking at the static page, we can execute those in action. So that's pretty much it. So you should be able to follow that through. So how many people have IPython notebook working? Or how many people don't have it working? Oh. So you just click on it, or yeah, and then say apply. It should work. So even if you don't have that, as long as you could do IPython and enter. It should open the browser. or it should say open this link in a browser. So in my case, I'll just close it again and open, so you'll know. So if you run that command, if you have notebook, then it should basically first spit out a lot of text like that. In my case, it opens a browser, but if it did not, then it usually tells you to go to a specific link, which is here localhost 8889. So if you just open a browser and then copy paste that link, it should work as well. So if you see, it's actually just that link. So you can install it as we go ahead. And once you actually have this working, you can just open a notebook and do it. But if you don't worry. Like if you think you can just type in the commands, it's a bit difficult, but it should be fine, I guess. In that case, you can do what you did before, which is just open IPython again, which just opens the console, interactive Python commands. And let's say we do that, which is mbpa2.tutorial _suite import star. If it's running, it's a good thing. So does that work for everyone? No, yes? How many people got that running without errors? That's good.
How long is it supposed to take?
Which one? Sorry?
How long is it supposed to take?
Oh, to finish, return the, usually, I don't know, like less than a minute for sure. If it didn't spit an error, that's good. If it's running, it's good, because it's just how powerful your computer is. So I'm actually going to go do the exact same thing in a notebook, so it's easier for me not to type, but you can just copy paste that from the browser window I showed you, which is that. So let me just go over the notebooks and so that we can. So what we are looking at is the tutorial datasets. So what I did just now is just imported the tutorial suite, which is just for the tutorial, so I don't need to do anything. But the basic idea is that, let me see first, you can just do clear our output. So what we did in the first line is just imported the whole set of tools. And then for IPython notebook, you just do control and enter, and that executes that code. Whereas in the console, you can just like copy paste that. I'm gonna show you like the easiest way to do that. So for example, so if you do something, if you type in something like, it's called cpaste, and enter, it lets you paste code from your copy, Control V, Control C, Control V. So I just copied that, and then I pasted that. And you do another line carriage, like enter, and then if you do 2 hyphens and enter, it executes it as well. You can also do it by just doing the percentage and paste. Mostly it should work. So did that make sense? So if what you can do is, you can go to the tutorial, even the ones who don't have IPython notebook, just copy that. I just clear the text, but it's do the paste. So that should work, right? Does it make sense? So just copy whatever you see in the browser and then paste it in the console. Mm-hmm. So I'll just show you what I copied. So I just copied that. So I think this can handle these prefixes, I suppose. So, and then you just like do copy and then you just do percentage paste and it should work. Did anybody have problems with doing that? Oh, do you want me to look at that? Yeah, you copy everything like from the beginning. Anybody else have problems with doing that? So I'm going to go ahead with this. So that's easiest way to copy the stuff from the browser and then just run it on your own in the console. So we did that, right? So let's see. We're just going to, so this is just an array of like ones and zeros and twos and fours. So I'll just show you how to make a data set out of it, which is very simple. Just like say DS dataset. By the way, when you half finish the function or the object name and then do tab, you can complete it if it's only the option there left. And then do data, which we just initialized as 11120031140 matrix or an array, and do that. It actually just created a data set with that array as the data inside it. We can look at the shape of the data set by just typing in ds.shape. And if you want to explore, you can also say ds dot and then do a tab. It tells you what all you can look at. Some of them might not be available because we haven't told it what the samples are or the features are. And also Control L usually clears the screen if it's cluttered already. So if you can do ds.shape and you get 4 by 3, which is the initial matrix or array we use, that's good, right? So we can do things like ds.n features, which is number of features it has, or you can do ds.n samples. It gives us the number of samples. So these are like basically easy way to access the number of voxels it has or number of time points or samples a data set has. So that's the basic thing. And then if you go down to, I'll also like follow this tutorial. So you just can access all of these things. And another thing is if you want to access the data itself, you can say ds.samples. And that returns an array, which is the actual data stored inside the data set, right? So these are the main simple ways of accessing what is inside the data set. You can also say print ds, which usually prints like what it is. And once we add more and more information to the data set, we can see it actually prints like a good summary of it, like what is available and what is, like what sample attributes it has, what feature attributes it has, what the data set attributes it has. But right now it doesn't have any of those. It doesn't print anything. So that's that. That's one of the key things. And I mean, I'm not going to go through every step because you can do it on your own. And I'll just go through the critical steps that kind of introduces you to the basic concept. So you can see here that you can initiate a one-dimensional array and then use that to start a data set, but it always makes it into like at least 2 dimensions with the last dimension being 1, right? Or you can initiate an array of 4 dimensions. It keeps the 4 dimensions, but it treats the last two as part of each feature. So in this case, for example, this data set, even though the array is a 4-dimensional array with 3 by 4 by 2 by 3, the first dimension, which has 3 things, are considered samples. The next dimension, which are 4 things, are considered features. And the last, however many there are, like 2 by 3 here, are considered like each feature is a 2 by 3 dimensional, or actually 2-dimensional, which has 2 times 3 elements in it. So, but these are not important for fMRI data sets because these are essentially built in to add more complicated data types. So forget about that for this particular case. And we know we talked about what samples are, attributes are. So we're gonna do this now, which is we're just gonna add a sample attribute, an arbitrary one at that. So you can just copy, paste only the first 2 lines, which are the actual commands. So copy that and do paste. So what we did there, I hope you can see the weird blue font I had. Well, I'll go back to the website. So what we did there is basically we said, okay, DS is our data set, which we just initialized, .SA, which is a short form of sample attributes. So what we're doing here is we're going to add a new sample attribute called sum attribute. So we just gave it a name, which is sum underscore at. So it's a string. And we just said that attribute contains these values. So remember we have 4 samples. So one key requirement is each of those samples should have that attribute defined. So in this case, since we have 4 samples, we just define that sum attribute as 0, 1, 1, 3. So that's the main key requirement. So it forces you to define attribute for every sample attribute for every sample. And if you're familiar with dictionaries in Python, this makes sense because these are exactly like dictionaries in Python. But if you're not, that's fine. But what a dictionary does is it maps a key, which is typically a string or any variable type, to another thing. So you can always look up like you do in a dictionary. So in this case, we are just saying some attribute is the key of the sample attributes, and the values it points to are the actual numbers we want to store. So in an fMRI dataset, these could be like ds.sa of, let's say, tr number, tr underscore num, and then you can just give an array of like 0, 1, 2, 3, 4, and these are like the trs of those samples, right, when we acquired. Another thing is you can like look at what keys are available. So that's what you did when you copy pasted ds.sa.keys. So ds.sa is like dataset sample attributes, and .keys gave you like what are the strings or the keys of sample attributes there are. Since we just added 1, that just shows up here. And you can repeat exactly the same thing with featured attributes. One thing really important to keep in mind is the number of things you assign as the values here has to match the number of features for the featured attributes and number of samples for sample attributes. That's all the thing. Which makes sense because you want to define a particular property for each of the sample attributes, right, or features. You can look at these or not because they are very Python specific and what it means. But the other cool thing you can do, which might be useful, is ds.sa.unique. So if you copy paste that in your IPython console, I'm just going to clear my screen. So I don't know how many of you noticed, but so you can see we actually have 4 sample attributes for that sum attribute. But then when you do .unique, it tells you like how many of them are unique. So one place where this can be useful is, for example, your experiment has faces and objects and rest. And because you say you have like 100 samples in your experiment, and then a bunch of them are faces, some of them are objects, and some of them are rest. You just want to see like what all conditions there are. You can just do dot unique, and it tells you like faces, objects, and rest. So you know like what are the unique sample attributes they have. So let's go back to this, and as I was saying, if you just assign like a single number, it complains because you actually have 4 samples and you need to give 4 numbers. Or if you give more, it also complains because you don't have enough samples to give those attribute values to. You can also give not just numbers, but also like a text. So for example, this could be useful when you say you have categories. So you can say, my 4 categories are 1, 2, 3, and 4. And so that defines that sample each case. And again, as I said, you can do the exact same thing for feature attributes, but you have to make sure they have the same number of features and samples. Features. Number of features match the number of feature attributes you give. And you can also give the attribute to the whole data set. Forget about the glob, but we'll just do this. So don't copy paste that for now. So if I do ds.a, which is the attribute for the whole data set, currently it just says an empty thing. So it's like there is a framework, but there is no items in it. So we can do something like, I don't know, let's say subject. So it's a string, and then I assign 1, 2, 3, 4. So now it actually takes that in. So it actually has a attribute called subject, and the value is 1, 2, 3, 4. And now if I print, I'm just going to add a feature attribute as well, just for the sake of it. Yeah, .fa is a feature attribute, short form. So we have added the feature attribute, a sample attribute, and dataset attribute. And once you have that, you can just say print ds. Now, as you notice, we have more printed. One, so it's a dataset, and it says the actual samples or the data inside it, which is 4x3 init64. And it says it has a sample attribute, which is sample attribute, or some attribute, and it has a feature attribute, which we just added, and it also listed like the dataset attribute, which is a subject. So if you actually have more, it just lists them as a bunch of strings concatenated by a comma. So you can look at what's in the dataset that is already stored when you loaded stuff into the PyMPA. Is everyone with me until here? Cool. So that's the basics. So basically, you can create an arbitrary data set. You can add a lot of attributes. So it's a very abstract concept at this point. So I'm not going to go through these for now because these are Python stuff. So you can essentially access like different chunks or parts of an array without accessing the whole array using these things called slicing and indexing. But this is exactly what Python uses. So if you know Python, you can easily do exact same thing with the dataset, and you can work without. But for now, I'm going to skip that. If you are interested, you can just like go through the exercise step by step, and you'll see it. So I think that probably covers the basics of what a dataset is. Hopefully, if you keep going down, there is a section called load fMRI dataset. This is probably the most important part because we will know how to load fMRI datasets you want to work on. So this is going to be tricky. So if you have already downloaded the tutorial dataset, I would copy that tutorial dataset into the folder you opened the IPython from, or wherever you downloaded your IPython notebook. So or you can actually try to, first try to copy paste this the first line or even the second line, for example, and see if it works for you. I'm pretty sure it doesn't work for me, but who knows? Well, it did. So how many of you tried that and it worked without problems? Oh, cool. Oh, right. So, but do you have the, let's see. Did you guys download tutorial data zip file? Not the hyperelement, but the actual tutorial data zip file. And if you unzipped it, it would contain a folder called, like, I think Hackspy 2001 in it. So, if you downloaded the data and then unzipped the data set, you'll have a folder of all the data you need. And so basically, if you have the data downloaded and unzipped, and you know where the location where you unzipped the data, I think we can proceed. Otherwise, how many of you have the data downloaded and extracted? And do all of you know where it is extracted? So if you know that, then it's much easier to work. So let's see. So I'm assuming you have the data set downloaded and then extracted. How many of you don't have that? I'm going to quickly help them. So I'm going to go, so assume that you have data on your computer in the virtual machine and you know where it is. If that is the case, you can, one neat trick you can do is you can take the tutorial data path and just point it to that location. So what it So if you just point that, so if you can just point the tutorial data path to that location. In my case, it's actually there, but it could be someplace else for you. And, sorry. And then repeat those two commands. It should work. Or so in my case, it's in the local directory, so I just said dot. So did anyone get to work? Okay, good. But so I just point to the actual tutorial, so we'll see what's actually going on. So what's happening here is, don't worry if you don't get it working, but the idea is you're just giving the location of your Nifty file. So if you have your own data set, you can just say bold underscore fname, which is a file name, to the string of where your file is. And in this case, it's actually just a Nifty file, which is bold.nii.gz. So don't worry about it if it doesn't work for you right now, but the basic idea is that you just point the file name, right? And once you have the file name, it's as easy as doing this, which is you call fMRI underscore dataset and then just give the file name. And to give you an idea of like what fMRI dataset is, you can just like type in fMRI underscore dataset, do a question mark. It actually tells you what it does, which is it creates a dataset from fMRI time series, and if you scroll down, it tells you like what the parameters are, which is samples can be a string or a Nifty image. So basically, in this case, what we did was is a string, which is the path to the file name. So yeah, you can just like add a string and just load it as a fMRI dataset. So how many of you got the dataset loaded? Okay, how many of you actually see some Nifty file locally somewhere in your virtual machine? So yeah, if you actually see some Nifty file on your virtual machine, you can just load it as fMRI underscore dataset. So if you don't actually have that working, don't worry. I think you can just follow it over the website, and it's as simple as that. But the basic idea is if you have an Nifty file, you can just load that by calling fMRI dataset with the file name. Once you have that, then we can do what we did before, which is just try to print the dataset. And then it tells us what's actually loaded. In this case, I have a dataset with 121 TRs and 163,840 voxels, which is basically the full Nifty volume. And it has time coordinates, which is like TRs. Time coordinates are, I think, the actual time points, and time indices are like TRs. So just like one is integers count, and the other one is the milliseconds or whatever the scanner recorded. And it also loaded the feature attributes, which are voxel indices, which are in the Nifty image, the XYZ coordinates. And it loaded a bunch of dataset attributes. I don't think you need to know all of them, but some of them are basically the affine transformation that has been stored in the Nifty header. So basically, it loaded most of the things that might be useful from the Nifty file and put it in the dataset object. So you can do all the things we did before, which is try to find the number of features or number of samples, and so on. So are you guys clear on what we did? So you can also look at like what the indices look like. So for example, you can say ds.fa.voxel indices, and it actually prints the XYZ coordinates for all of the features. So you can also look at sa.time coords. So these are actually, if you see, it's in seconds and they are the TRs. So because the TR of 2.5 seconds, the first sample is acquired at 0, the second one is acquired at 2.5 and 5.0 and so on. So you can basically explore all of these things. And time indices would be the TR numbers in integers. So this is all pretty simple. The other thing I think you should know is when you try to look at what is in the dataset attributes, wow, that's a lot of them. So we have a lot of those dataset attributes, which are image affine, image header, and so on, which are all what Nifty stored, which are not interesting to us. But one thing that is going to come up later is ds.a.mapper, which is one of the attributes of the datasets here. So if you look at that, what it shows is it's a flattened mapper, which is exactly what I said before, which is the Nifty file is a 4-dimensional dataset with 3 dimensions of features, right, XYZ. And the first thing it did when it loaded the dataset is to flatten the 3 dimensions into 1 dimension of features. So if you notice, we have like what, 40 times 64 times 64, which is exactly, at least it should be, the same number of features. So it just basically flattened the 3-dimensional data into 1 dimensions of, so that's what it does. So we know what has been done to the data set when it loaded it. So that's why it's important to know what's in the attributes file of the data set. You don't have any of these? Yeah, because I think the DS I have is the one I loaded from the Nifty file, and the DS you have is probably the one we created before, which doesn't have any of those attributes, right? So this is a new dataset, DS, which, yeah.
So if it's flat enough, how do you know which voxel is which number?
So that's why we have, as I said, the feature attributes, which, for example, if you want to know what the first voxel indices are, you can do that.
Oh, but that's a feature attribute.
Yeah, so each feature gets like a feature attribute stored, and then you can see what that is. So the first one is not surprisingly coming from 0, 0, 0. So we're going to see later how this mapper is going to be useful for you to do the opposite, which is when you have your data in this 2-dimensional space, go back to 3 dimensions and look at it as a Nifty file, right? So I think these are the basic way. Like you just load fMRI data set, it keeps most of the things it can understand, like in the Nifty header, number of features and so on. So you can play with that. The other important thing is, so if you notice, we just gave it a single Nifty file, and so it loaded all the voxels in the Nifty file, right? But typically we don't want that. We usually want only data from the brain or gray matter for that matter, because everything outside is useless. So one way to accomplish that would be just point it to a mask file, which could be another Nifty file. In this case, it's the mask of VT, ventral temporal cortex, which Jim talked a lot about today. And So just give it the mask name and so that's basically where the mask file, the VT Nifty file is in my case. And then do the exact same thing, but this time, as you probably already noticed, we have given the name of the dataset, which is the bold FMRI, and the mask name, mask file name as a mask attribute. So we just said mask equals vt.nifty file, right? And now if you look at the DS, I'll just clear it so that you can all see. There are only 577 voxels. And because the mask only has 577 voxels in it. So instead of loading the whole data, you can actually load only the gray matter mask or a particular ROI you're interested in and so on. Is that clear? So, right? So this is going to be pretty useful because you never want to load the whole data set because you use waste of space and everything is noisy outside the gray matter most of the times. Let's see. So if you actually type in the ds.aa.mapper, you can notice that now we have two things rather than the flattened mapper itself. And there is something called chain in the beginning. So what it means is, when we loaded the whole data set, all it needed to do was convert the three-dimensional block of data in Nifty into a two-dimensional array, which is just flattening the thing. But now since we gave a mask, after flattening that thing, it also needs to sub-select which voxels are from that mask. So, and for most of this case, you apply one mapper first and the second one after. So it just flattens the full Nifty file and then selects the voxels from VT. So we can also look at that by doing this, which is, so we have two mappers or things here, like mapper one, which is the flattened mapper, and mapper two, which is the feature selection mapper. What you can see is essentially the selection is happening here. You only see like falses, but because there are so many voxels that are not part of the mask, but there are some true values in there which are actually the voxels that are part of the mask, which are only 500 out of like 163,000, so you won't see it here. One way we can look at that, if you're interested, is to do so that's the mask, and then say sum. So we know like how many true values are there in that, which is 577, which is exactly the same as the number of features it has, right? So that's another thing. Let's see. In addition to doing, well, so now actually we added a mask, so we can also do something which is, let's see if I can make it work. So something called targets, which are typically in the classification situation, these would be your labels for each TR. So you can actually add them here, or you'll probably see later where you can just have a design file and then just load that information from the design file. So all of this would be available, I think, or you can see them in the tutorial. But for now, like you know how to load the data set for a specific mask. So I'll just move on to the next important concept, which is mappers. So I kind of alluded to that, which is in terms of flattened mapper, static feature selection mapper, but let's see what they actually mean. So hopefully we got something out of the first notebook. So basically, until now, we just loaded the data set. We didn't do anything to it, which is pretty much useless because you just like changed the format and looked at it differently. So one of the main concepts of PyMPA is the mappers, which are, if you know mathematics, it's like an operation or operators on the data set. So a mapper is like any object which essentially operates, results in a different data set. It could look different. For example, in this case, I can have a mapper that takes in a data set with a bunch of features and transforms it into a new data set with a different number of features. And the mapping could be something like a PCA. So you start with a bunch of voxels in VT, but you end up like mapping those into a bunch of principal components. So it could be that, but it's very abstract. So it can mean a lot of different things depending on how you define it. And as I showed, one of the mappers would be a flattened mapper. Another one could be a static feature selection, which basically selects a subset of columns and then keeps that in the new data set. Sorry, what? Usually, I think there is a particular kind of mapper called projection mapper, which essentially multiplies the data set with a matrix and results in a new data set. That would be a linear mapper. So actually, hyperelement is a linear mapper. So it is exactly that. It's a projection mapper with a specific matrix we derive from the data set and then apply it to a new data set, and it results in a common space data set. We will go through that, so don't worry about it for now. But this is another important concept. So I think the main things you need to know is like there is this thing called data set, which is your data with all the bells and whistles, like so you know what exactly each sample and feature are. And you can also like map things from a Nifty file into this array format and back to Nifty file after you do something in this PyMPA dataset format. And the second thing is mappers, which are most of the operations you're gonna do, like changing how the dataset looks or applying some transformation to the dataset. So let's go back to the notebooks. So you can actually go through this tutorial yourself, so I'm not going to like go through everything, but if you go back to the tutorial table of contents, the second thing is called getting data in shape. If you click on that, it opens another notebook. So here, you don't have to worry about it. I think most of the stuff we already talked about, which are flattened mappers and stuff. And one concept is, as I mentioned, chain mapper, which means it just like chains a bunch of operations together. So it applies them in sequence. Like in the case of a mask dataset, we applied the flattening first and then selecting the mask voxels later. It's kind of interesting because with these mappers, we can also reverse it. So for example, if you got your VT dataset and then you computed some value in each sample. So let's say you just averaged all the TRs. So instead of like we had like what 100 samples and 577 voxels, and I just averaged each all the samples for each voxel. So I'll end up with 1 by 577 dataset. I can do the reversing of this mapper, and it actually proceeds backwards. So what it does first is it remembers that it did the feature selection. So it maps my 577 voxels back into 163,000, which is the full number for the Nifty file, but only keeping values in those 577 voxels as non-zero and the rest of them as zeros. And then it applies the reverse of flattening, which takes this two-dimensional data matrix and puts it into a four-dimensional, so 1 by 40 by 64 by 64, which is what the Nifty file dimensions are. And that is pretty much exactly what a Nifty file is with the header information, and then we can just write a Nifty file out of it. I can show it. I think we're going to do that later. But for now, let's see. Since you don't have the notebooks with you, So again, we're just doing what we did before, which is loading the data from a particular Nifty file. In this case, I think this, wait, sorry. We already loaded the data set. So what we're doing here is we are loading attributes, which are, in this case, typically design files. So for example, if you have a design file already made for your JLM analysis or something, you can have for each TR the target or your condition. Like in this case, the conditions would be a bottle, cat, chair, face, whatever the stimulus is. And you can have another attribute for the same TR which can tell what run it is from. So for example, if your fMRI experiment has 10 runs, you can just say for the first about 100 TRs which belong to run 1, all of the second column could be like ones. So if you have a design file, you can directly load that and assign it to the data set as sample attributes. And that's what we are doing here. So once we loaded the design file, we can just say the same way we loaded the dataset before, which is fMRI underscore dataset. We gave the samples as the Nifty file. We gave the mask as a mask file name. But in addition, we can say targets as attributes.targets, which is what we loaded from the text file of design. As I said, these are like your categories. And then you have chunks, which are actually same as runs. And you can just say the first few TRs belong to run 1, and the second few TRs belong to run 2, and so on, the next few TRs. But then basically the more things you put into the data set, the more information it contains, obviously, and you can play with that later. So let me see. I'm just going to run everything so that if it worked. But anyway, but the basic point here is that once you loaded those attributes, you can see them as sample attributes collection. So you can see targets and chunks in addition to the time coordinates and time indices we saw before with the plain Nifty file. So I'm gonna skip most of this for now. So you can run a for loop and then load a bunch of subjects. Right now we are only loading one, so that's it. You just like run a for loop and then update your link to the bold file names and then just like add a bunch of subjects. You can just load it. And let's see, I'll just show you like another small thing that might be of interest. So those of you actually have the dataset downloaded and accessible, you can run these things. And one way to run, well, if you have a notebook, you could just do cell and run all, and it runs all the commands in it. But I'm sorry that you don't have it accessible for now, but you can do it later when you're home and install everything. So anyway, so once we have loaded the attributes like targets and chunks, we can do what we did before, which is look at unique targets. So this data set has a bunch of categories, and it shows us what are the unique categories are. And in this case, those are the objects and faces we used in that data set. And you can also look at the chunks, which are how many different runs, or in this case, it's just one TR is considered each run, so it's just 121, which are the number of samples in it. You can also look at the unique chunks, which in this case, there is only one type of chunk, which is chunk 0, or run 0. So you can look at all of these things. And then I think, let's go load a bunch of them. So assume that I have actually loaded it right now, but if you run this block, you load a bunch of runs. So in this case, I think there are 10 runs for this data set. And once we have that loaded, we can just like look at the summary. So what we're seeing here is essentially this data set has 16 samples and 577 voxels, which are part of the VT mask. And then each chunk is actually a summation. Basically, it's a combination of all the even numbered runs and odd number runs. So I'll go back to what I did here. So what you're doing here is basically run_ds loads the data for each run for that subject, and it appends into a list of those things. And vstack is another command which, if you have a list of data sets, so for example, you have bold1.nifty, bold2.nifty, you can just load all of them into a list. And if you do vstack of that list, it just combines them into a single data set and keeps track of the like chunks it has. So I mean, all of this will be actually very clear if you run it yourself, but I'm sorry, you couldn't do it now. But the idea is that you can load a bunch of runs from our experiment and then put it in a single data set. Once you have more than one run, you can also, so one of the commands that will be very useful is to run a dot summary of a data set. If you have a lot of information about the data set, it computes a lot of statistics as well. Like for example, in this case, you're looking at the mean target values for each target and so on, or how many of them there are. So in this case, there are like number of chunks. So there are 2 bottles per run, or 2 cats per run, and so on. And then it also computes the ordering. So for example, order 1 would be like how many times the bottle happened after cat or something. So all of these could be useful to make sure, excuse me, your data is well balanced. So in this case, pretty much all of them have, except this, equal number of like times one preceded or succeeded the other. And this is order 2 balancing. So all of this information is basically to make sure your data set has loaded properly and your data design is reasonable. I'm sure. So chunks are exactly like runs. Sorry, what? Yeah, it's like the sessions. Yes, sorry. So the reason that is important is because when you do classification analysis and when you train your classifiers on a bunch of sessions, it's always advisable to test it on a different session so that you don't carry over anything from the previous session except your experimental design, right? So, but I mean, for some reason the chunk stuck. I was very confused in the beginning too, like what do the chunks mean? Like we call them runs or sessions. I would say it the other way around, which is you would then define chunks as your event blocks or something, right? So if you have like event-related design where you have like a bunch of events and then you have some rest and then you have a bunch of other events, and so you can probably define those blocks as your chunks, even though you ran the whole experiment in one session. Actually, I might be misleading you because at least in the experiments I've run, it's typically you have at most 9 to 10 minute sessions or runs, and you give a break, check with the subject if it's doing okay or he or she's, and then you run a second run, right? And these are like counterbalanced and so on. So those are what runs are. Essentially one sweep of your acquisition, but it's not strictly enforced. So you can, for example, for the movie data, we actually say a run could, because they watch the movie continuously, I can arbitrarily chunk them up and say this is one run. The first 10 minutes is one run, the next 10 minutes is a second run. So it depends on what you give when you loaded the data set. You can say the first 100 TRs are run 1, second 100 TRs are run 2. So So the chunks are going to be necessary for two reasons. One is when you do cross-validation for classifications, when you run, if you run cross-validation command, it automatically assumes that you're cross-validating over chunks. So which means if you have 10 chunks, it automatically trains on first 9, tests on the last chunk, and then it runs on the everything but the second, or last but one, and then tests on that one. So it does the cross-validation automatically, assuming chunks are your separate data set sessions. So that's the reason it is important. So yeah, once you have the data set loaded, you can like look at everything. And then there are a bunch of processing steps, like you can do detrending, but I usually do it during my like pre-processing and using AFNI or FSL, because that's, if you run a GLM analysis, you have to do it anyway. But you can do this within PyMAPI as well. And you also notice that they have this thing called chunks attribute as chunks. That's actually other place where it could be useful. When you're detrending, you want to remove the linear trend from within a session or a run, right? So the chunks are also useful here. So it fits the trends within that session. Because once you stop and start the scanner, everything could be different. So that's another place it could be useful. And detrending is also, as you note, I don't know if you notice, it's actually a mapper. So it, again, does something, operates on the data set. And since it's a mapper, which is a separate object from data set, you can apply it to different data sets. So you can define a detrender, in this case, a polynomial trend removing thing of order 1, which is linear. And then you can apply it to any data set. In this case, FDS is the data set we loaded. And then you can say fds.getMapped, _mapped, and then give it that mapper. What it does is it applies that to the FDS and returns the detrendered data set, right? And once we did that, you notice that you can look at the .mapper, a.mapper. It actually lists that as a mapper that has been applied. So it keeps a history of what this data set has been gone through. So in this case, it would be flattening from nifty 3 dimensions to a 1-dimensional feature set, and then feature selection, which is the mask we applied. And then now, if we apply the detrending, it also keeps history of the detrending. So that's a good thing to know, because we want to know like what has been done to the data set to interpret it properly. And normalization is basically z-scoring. So this is something that pretty much a standard thing to do when you do classification. The reason being, most of the classification algorithms that are developed outside, obviously, neuroimaging are built under the assumption that your features are have similar or comparable means. Because if you look at it, like when Jim talked about the representational spaces, so let's say you have like 3 voxels and you're plotting your data set in that 3 or 2-dimensional space. If one voxel always has like 100 times the value of the other one, and if you look at the vector, it would be terribly close to that dimension. So it kind of like skews the data. So one thing that you do to satisfy a lot of the assumptions about classification algorithms is to make sure every feature has the same range of values and preferably 0 mean. So z-scoring is essentially that. It just removes the mean from each feature and divides it by standard deviation. So the standard deviation after z-scoring of all your features or columns are going to be 0 and 1. And again, this is a mapper. So you can define a z-scoring mapper. And so this is the next important thing here, which is in the fMRI, we don't have to just do removing mean, but we can do something more clever, which is we don't remove the mean, but we remove the mean during rest blocks. So rest would be our baseline. It's something like person signal change in a way. So you can actually tell them that, which is the parameter estimates for the mean and standard deviation to remove from each voxel should be taken from the targets called rest. So what it does when you apply that is it takes all the rest samples, averages them, and finds the average of those rest samples for each voxel and subtracts that from the samples for all the actual data that are not rest, like your bottles and whatever cats and stuff. And it also takes the standard deviation from the rest blocks and then divides the other blocks data with the standard deviation computed from the rest blocks. So it's sure. Okay. But so anyway, so you can do this to a data set and then z-score them. So I'm not going to go through the classification part. I'll just like introduce how you can do hyperalignment. I guess you guys listened to it this afternoon. So let's see if that could be taken out. But anyway, so basically what the basic concept is, you can load your data set. You can do a bunch of basic operations like normalizing them with z-scoring. Once you have the data sets in place, you can either do classification, which is pretty simple if you follow the tutorial, or run hyperalignment, which is as simple as actually running a classification. So I'm going to just go through that for now. And I think for the time being, I will just show you the static page so it's easy and faster to look at. So if you want to look at the hyperalignment example, you have to go back and go to the documentation, and they have example analysis and scripts. And I think the last section is hyperalignment for between subject analysis. If you're on the page, you can just follow me or just look at it here. So the basic step would be, the first line always has to be this, which is mvpa.suite.import. It imports asterisk like star. It imports all the basic tool sets for MVPA2 package. Ignore the verbose level, which is just what to print when it's running something. And basically this chunk is all loading data set or runs from a bunch of subjects. So you can ignore that for now. So all it's doing is just, I think in this case, loading like 10 subjects data from the experiment I just showed with categories like cats, scissors, bottles, and so on, and faces. And here I'm just defining a classifier. In this case, it's a SVM classifier, which is pretty standard and usually works pretty well without tuning it too much. And I'm also, instead of running the whole hyperalignment on the big mask like VT, I'll just select 100 voxels with some criteria. And that's something you can define on your own. I think in this case, we are using ANOVA as the criterion, but that's up to you. And you don't even have to select that if your data is like nice and clean, all coming from gray matter voxels and it contains information. So to run an actual vanilla classification, all you need to do is define something called cross-validation, which I was just mentioning, and then tell it like what classifier you want to use. In this case, this would be your SVM classifier we defined before, and what kind of folding you want to use, which would be n-fold partitioner, which means if you have 10 runs, you select the first run for the test, use left out 9 runs for training, and then test it on the first run. But you repeat that with every run as a test run. So if you have 10 runs, you will have 10 partitions or 10-fold cross-validation. That's all it means. And error fx means what kind of error you want to compute. In this case, mean match accuracy is like the total accuracy across all categories that we correctly predicted using the classification. And so what's happening here is basically running that cross-validation for each subject separately. So ds underscore all is a list of individual subject data sets, and SD is one of the lists selected, and then you pass it through the cross-validation we defined here, and what it spits out is accuracy for each subject. So trained on 9 runs, tested on the left out 10th run, and do the folding and average that. So that's pretty much it. So, and then you would get accuracies for that mask. If you want to do the between subject analysis, you have to do a little bit tricky one, because instead of cross-validating over sessions or runs, you do the cross-validation over subjects. So if you look at it, it's pretty much exact same code, except that you are saying that the enfold partitioner now works over subjects. So, and then run the classification as is. So this time it trains, if you have 10 subjects, it trains your classifier on 9 subjects and tests on the left out subject which did not participate in the training. Now, if you want to apply hyperalignment, so there is some trick here because we are using the same data for training hyperalignment and testing this on, but in the case we published, we use movie data. So you can just use the data from the movie to run the hyperalignment and apply it to the second experiment. The reason we have it a little bit complicated here is because we don't want to train the hyperalignment on the same data set and test it on the same data set because that would be cheating, right? So you can kind of ignore this, but what we're doing is we just define the cross-validation as before with subjects as cross-validation factor, and then we're just looping over each test run. So essentially I will say, okay, I'll just test my validation on, let's say, run 1, and we only derive the hyperalignment on the left out 9 runs. So we're going to use the 9 runs for deriving hyperalignment and also training the classifier. And the first run is going to be totally out of this loop and be only used for testing the between subject classification. So all this is doing is just trying to separate those things and make sure they are different. The actual hyperalignment is happening actually in these 2 lines. So I just defined hyperalignment as hyper as hyperalignment. So you just need to run this one line, and it defines a hyperalignment object, which is like a mapper in the end. And then you call your list of data sets with the hyper, and that's it. That basically spits out those matrices which Jim talked about that rotates the subject space into the common space. So essentially it's as easy as this. So you have your list of data sets and then call it with hyper. And this is going to be a list of mappers, which are basically matrices that you multiply new data set with to transform that into the common space. So if you look at it, so the hype maps has the list of mappers, and what we do is we apply that to the test data. Let's see. So we're taking the DS test, which is the left out run. This is here. It's also doing feature selection. We can ignore that step, but once we have the feature selected, we take the test data set and the hyperalignment mappers, which we got from the previous step. And for each subject, we apply that hyperalignment mapper, which is the first one in this case, for the first subject, and do dot forward, which applies the mapper with the data. And then it spits out the data for that subject after the alignment. Does that make sense? So it's basically you define the hyperalignment, and deriving the mappers is basically giving it the data you want the hyperalignment to be derived on as a list of subjects. And it just spits out for the same list of subjects a different a mapper, which is alignment transformation. And then when you want to apply, you just like say that subject's hype map dot forward and the new data set, and it spits out the data in the new space. Depending on the size of your ROI, it can take anywhere between like a few seconds or minutes to maybe half an hour if you have a really big ROI. And rest of it is basically validation. I don't think it's basically making sure we don't use the same data for training and testing and so on. So I hope, you can just like, if you have your data cleanly separated between like say 2 different experiments, you can just give the first experiment to hyperalignment here, get your mapper, store them if you want, and then just run it on a second experiment and see if it works. If you just run the between subject classification after you do hyperalignment, I'm just going to show the results. You can see that between subject classification after anatomical alignment is around 42% for this experiment. Within subject was 57, and between subject after hyperalignment was 62%. As Jim mentioned, this is because we have more data doing between subject classification after hyperalignment than within subject classification. You can also do similarity structure analysis, which I'm not going to go through. And I'm also going to like show you how easy it is to do the whole brain hyperalignment in this framework. So let's see if it's up here. I'm going to skip all that, which are not really critical. But so the whole brain hyperalignment is actually called searchlight hyperalignment in PyMBPA, because we use searchlights to do hyperalignment. And again, it's as simple as this. So this is all defining the classifier and cross-validation. But the main part is here. So instead of defining hyper as hyperalignment, now I'm defining SL hyper as a searchlight hyperalignment. And this time you have to give a bunch of parameters, because we want to know, one, the radius of the searchlight you want to do hyperalignment on. So here I'm using 3 voxel radius, which is standard in the field, I guess. And the other thing is you can also give it the feature selection. So because we are using searchlights, sometimes you can basically grab voxels from the white matter or something. So you want to kind of clean that up. So we have an inbuilt feature selection which takes care of that, but you don't have to do it. You can just essentially ignore all of these things and just give the radius of the searchlight, and that's the required arguments. And once you define the SL hyper as searchlight hyperalignment, and it's the same thing as before, which is you just call SL hyper with your list of data sets, which you can use for training, or a particular experiment you want to learn the parameters on. And then again, it spits out the same thing, a list of mappers. And then actually applying the mappers is also the same, which is you take for each subject that particular subject's mapper and that particular subject's data set, and then do dot forward, and it gives the data in the common space. So these steps are identical to what we did before, but this time it does this searchlight hyperalignment and aggregating those local transformations into a big matrix and so on behind the scenes. And once we have that, we can run our validation tests and so on. Here we're just like showing how similar the results are with searchlight hyperalignment or the regular one within the VT. So I think we are out of time, but the basic idea is like once you have your data in the PyMBPA format, it's as simple as 2 lines. One, you define your hyperalignment with all the parameters you want, and then run it. And it spits out the mappers, and you can just apply to whatever you want. So if you have any questions, I'm really sorry it's not very detailed, but one good thing is if you don't take anything out of this session due to the data, so you can just go to that link, and you can basically just follow the tutorial. And it's pretty well done, and it's also updated, by the way. So PyMBPA releases like maybe once a year or so and fixes bugs. So whenever there's a new thing, we usually try to update that in the tutorial. So, and the other thing I actually did not mention, but did not actually show you, but is very critical, is if you have your data set in the OpenFMRI bits format, then they also have a helper function, which is basically you can just call that, like get, I think, OpenFMRI data set or something, and then you can just give it subject name and number of runs you want to import. It basically imports all the data and all the experiment design and tasks and stuff. So it makes your life easier by just importing a standard format, data sets in a standard format like OpenFMRI. You can also see that in the list of tutorial table we saw. One of them is that, loading fMRI data sets from OpenFMRI format. So that's pretty much it. And
So very much. An enormous amount of work that you put into building these things, and more than anybody could possibly absorb in this amount of time. And we really appreciate it, because these things are all available to us now.
Yeah, thanks. But yeah, go to the PyMBPA website and just learn it for yourself. It's pretty easy, actually. If you have any questions, I can just take. And if you have, actually, if you want to run this through, and if you have problems like installing, or if there are errors spitting out, I can also help now. I should be here. So, thanks.